Okay, so in this video we want to review the process of completing the square. So one of the main reasons we might want to complete the square is to convert a quadratic equation from this expanded out polynomial form ax squared plus bx plus c into turning point form, which, as we know from the last two videos, turning point form is a much better form for us to graph the function from. Now, it's perfectly possible to graph the function without converting from polynomial form to turning point form, as we saw in the previous video, but it is an option to convert to turning point form. It's also an important technique to think about, if you're using your CAS, for example, and sketching a quadratic and you want to know where the turning point is, rather than using any of the functions in the graphing screen, so rather than using, analyze graph and maximum point, or analyze graph and minimum point, or graph trace, where you'll always only get decimal values, you'd be better to actually just get your CAS to complete the square for the function so that you can see it in turning point form, so that you can therefore state the coordinates of the turning point more accurately. So that might be another place. There's also other areas of the course in which we need to complete the square. So when we're working with graphs of circles, you might recall that from last year as well, needing to complete the square. So let's have a look through this video at reviewing that process. Hopefully it'll come back to you as we look at it here. So when we complete the square, the key thing that we want to identify in terms of the form that we're trying to end up with is we want to end up with a perfect square. X plus or minus a number all squared to create that turning point form. So we want to go from this polynomial form where we have a number times x squared plus a number times x plus a number to this turning point form where, okay, there's some numbers around it, but the key feature of it is that perfect square. And if we can focus on creating that perfect square, everything else will fall into place around it. So the key idea is to understand what happens when we expand out a perfect square, and therefore being able to recognise the patterns of a perfect square in the expanded form to be able to factorise it back to the perfect square. So when we expand x plus a all squared, we get x squared plus 2ax plus a squared. Okay, just to confirm that, obviously x plus a all squared is x plus a times x plus a, and when you expand that out, you'll do x times x, which is x squared, x times positive a, which is positive ax, a times x, which is plus ax, and a times a, which is plus a squared. And so we have ax plus ax in the middle there, and so they will always collect together to be two lots of ax, and then plus the a squared on the end. Now, the only thing that will be different, if it's a minus in the bracket, x minus a all squared, so minus a minus here, when you expand out those brackets, you'll still get positive x squared, but you'll get negative ax, and you'll still get positive a squared on the end because it's negative a times negative a, so still positive a squared. So the only difference if it's a minus is that you'll have a negative 2ax. Okay, so if there's a minus in this bracket here, there'll be a minus here. Okay, but if it's a plus here, it'll be a plus here, and everything else stays as it is. Okay, so key patterns we want to look at. The key thing, well, couple of key things. The first thing is, if I look at this coefficient of x, okay, and this constant term at the end here, okay, if I want to get from the coefficient of x to the constant term, I'm going to need to halve that. If I have positive or negative 2ax, sorry, forget the x, just the coefficient, positive or negative 2a, when I halve it, I get positive or negative a. And then when I square positive or negative a, I'll get a squared. So I want to halve and square the coefficient of x in order to work out what's happening with the number on the end in the perfect square. That's one of the key strategies we need. And to be able to see that pattern, to recognise that we have a perfect square. And then the other thing that we want to know about is this one, which is if I then want to factorise, okay, I'm again going to take that coefficient of x and I'm going to halve it to work out what goes in the perfect square bracket. And I always refer to halving that value rather than taking the square root of that value, because when you take a square root, it's not clear whether you need plus or minus. So when you think about halving the coefficient of x, if that's a positive number there, it'll be a positive number in the bracket. If that's a negative number there, it'll be a negative number in the bracket. So it's better to think about it that way in terms of getting this sign right in your bracket. Okay, so those relationships are important because they're what we're going to need in order to generate our perfect square if we don't have a perfect square. So when we're completing the square, we are aiming to create a perfect square even if we don't have one. So x squared plus 2x plus 5 is not a perfect square. And we can be sure of that because if I was to halve and square 2, I don't get 5. Okay, so what I want to think about is okay, it's not a perfect square, but what would, plus 5 on the end means it's not a perfect square. What would it have to be to make it a perfect square? And so again, it's about taking that coefficient of x and halving and squaring. Sorry, let's try that again. Halve and square it. Halve and square. So half of 2 is 1 and 1 squared is 1. So we would need positive 1 on the end there to make that a perfect square. And then if we think about how we then factorize that, we know that the number in the brackets here will be half of that one. Okay, so we're going to halve it, halve positive 2, so plus 1 here. Now, they won't always be the same. That's just a coincidence of the fact that 1 squared is also 1. Okay, but in this case, if it was a plus 1 on the end instead of a plus 5, it would be a perfect square. So when we want to complete the square, we simply basically say, okay, well, we don't like that plus 5. Let's just shuffle that to the end out here. So let's just move that over here and leave it, and we'll worry about it later. What we want here is to have a plus 1. We know that that makes it a perfect square. However, the minute I wrote plus 1 there, these things are no longer equal to each other. I can't just add 1 onto something and expect them to still be the same. Okay, so I'm going to also take away 1. Because now I haven't actually changed anything. I've added in 1 and I've taken away 1, so I've actually only added in 0. But what this enables me to do now is to focus on the perfect square, okay, which becomes that. So x squared plus 2x plus 1, we know becomes x plus 1 all squared, okay? And then outside of there, we still have this bit, okay? So we still have, sorry, that made the red go. Let's see if it stays red. No, we'll stick with it, leaving it. So we now have these bits together out here, a minus 1 and a plus 5. Okay, so it's still going to be negative 1 plus 5, and you can simplify that at that one point. So the perfect square is x plus 1 all squared, and then we've got minus 1 and plus 5 out there, so plus 4. So this expression can be written in turning point form as this, through the process of completing the square. Okay, so we create that perfect square and then we just deal with whatever numbers are left around it. One of the really key things is when you complete the square for a non-monic quadratic. So what I mean by a non-monic quadratic is a quadratic where we have a coefficient of x squared, so ax squared plus bx plus c, where a is not 1. Okay, so here we had 1x squared. That was a monic quadratic. If it is a non-monic quadratic, if that was 2x squared or 5x squared, or even if it was just negative 1, negative x squared, it's a non-monic quadratic. And the first step that you must do is you can only complete the square for a monic quadratic. So you must factor out the coefficient of x squared, even if it's not a common factor, even if it means making fractions. It's no option because we have to create a monic quadratic, 1x squared, before we can do the completing the square process. Okay, so let's just work our way through a series of examples here to just practice and review that. Write each of the following in turning point form and hence state the coordinates of the turning point. Okay, so we want to have a look at this first example, part A. So we're thinking about that plus 2. If we were to halve and square that, it is not negative 8, so this is not a perfect square. So let's create that perfect square. So I'm going to leave the x squared plus 2x. The negative 8's not helping. I'm just going to write it over here and worry about it later. And we want to focus on what do we need to add in and take away in order to create the perfect square? So we've already done one with plus 2x. Halving positive 2 is positive 1, and 1 squared is 1. So adding 1 onto that will make a perfect square. And then we can't just add 1 in because we feel like it, so we have to also take it away. That there now is our perfect square. That's what we want. And that's going to factorise to x plus 1 all squared. Remember, we take this number here, the plus 2, and we halve it to get this number here. Okay, and then outside of the perfect square, so outside of the yellow highlighting, we've still got negative 1 and negative 8, so minus 1 minus 8, which is minus 9. So when we've completed the square, x squared plus 2x minus 8 can be written as x plus 1 all squared take away 9, which means it is now in turning point form, and so therefore we can now say that the turning point is at negative 1, negative 9. Remember, this plus 1 in here translates the graph to the left by 1. This minus 9 translates the graph down by 9. So the turning point is now at negative 1, negative 9. Okay, let's have a look at part B. So y equals x squared minus 4x. Let's leave ourselves room to complete the square. We'll just stick our plus 10 over there. So we want to think about halving and squaring negative 4. Half of negative 4 is negative 2, and negative 2 squared is negative 2 times negative 2, so it's positive 4. So we need to add in 4 to create that perfect square. So that's our perfect square now. And then we can't just add in 4 because we feel like it, so we take it away as well. And now we've got that highlighted section is our perfect square. So it is going to be x minus 2 all squared. So remember, halving that gives us the value in the bracket. Okay, so x minus 2 all squared expands out to x squared minus 4x plus 4. And then outside of there, we have negative 4 plus 10 minus 4 plus 10 is plus 6. So there we are in turning point form. So therefore, the turning point is at, so the negative 2 translates to the right by 2, so the x-coordinate of the turning point will be 2, and plus 6 translates up by 6, so 2, 6 is our turning point. Okay, let's have a look at some non-monic examples, part C and D. So in part C, we've got 3x squared minus 9x minus 4. Now, even if we don't like it, we have to take out this 3. Okay, so we're going to have y equals 3 times x squared minus 3x minus 4/3. Okay, nothing you can do about that. You can't cancel this out. The only time you can cancel out that 3 is if this were to equal 0, because then you're dividing both the sides of the equation by 0. But this doesn't equal 0, it equals y, and you want it to still equal y at the end here. You want to have y equals x plus or minus something and then plus or minus something. You want your final answer to still equal y. So you don't want to move the 3 over there. So you just need to factor it out. And the biggest thing you need to be careful of here, in fact, I'm going to write the 3 in big red brackets until I consciously expand it back out again. I don't know how many lines I'm going to need. It's really important. You'll make a mistake by losing the 3. And we won't lose the 3, you'll lose the brackets, and you won't have properly expanded it back out. Okay, so let's be clear what we want here. So we're going to have x squared minus 3x, and then we need to think about what we want to add in and take away. So to make the perfect square, and then we're going to have the minus 4/3. We'll worry about that later. Okay, we want to halve negative 3 and square it, okay, to make our perfect square here in these first 3 terms. So halving and squaring negative 3. Okay, if you need to write it down, by all means do. Negative 3 over 2 is halved, and then square it is going to give us negative 3 squared is 9, and 2 squared is 4. Positive 9 on 4. So we need plus 9 on 4. We need to add in 9 on 4 to make that a perfect square. And so then we also need to take away 9 on 4. Okay, so that highlighted section is our perfect square. Okay. And so it is going to be, remember, the coefficient of x, we halve that to work out what goes in the bracket. Okay, so it's going to be x minus half of 3, 3 on 2. Okay, then outside of here, we've got 2 fractions that we want to collect together. So let's get a common denominator there so we can do that. Common denominator will be 12. So this is minus 27 on 12. Take away 16 on 12. Now you might be able to do that in your head, which is great. If you can, you want to do that. So you might be able to think that through. Okay, that'll be 27 on 12 and 16 on 12 and negative 27 take away 16, etc. Okay. Okay, if not, write down an extra line, that's fine. Now, the place where you'll have made the mistake if you weren't careful about your 3 that you factored out would have been at this line here. You would have omitted those brackets because you would have been so excited about writing down a bracket for the perfect square that you would have forgotten that actually that perfect square is still within that larger bracket. Okay, so not worrying about the 3 yet, I'm just worrying about collecting these together, and then, and then we'll worry about the 3 at the end. So we're going to have x minus 3 on 2 all squared, minus 27 minus 16, that's going to be minus 43 on 12. Okay, now we're ready to multiply our 3 back in, so it's going to be 3 times that perfect square and 3 times 43 on 12. Okay, and this is where if you accidentally drop the brackets of the previous line, you'll have the wrong value here because you need to multiply by 3 again. Now, big hint, so I'm going to multiply that in, 3 times x minus 3 on 2 all squared. Every single time that you multiply that 3 back in, if you've got a fraction in here, that 3 will cancel down with the denominator of that fraction, always. There's a common factor of 3 in the denominator, and that's because you created that common factor of 3 up there when you divided by 3 in the first place. So I do not want to work out what 3 times 43 is and then try and simplify that fraction. I want to recognize that if I've got any number, if I've got any number divided by 12 and I times it by 3, the 3 will cancel down with the 12 to make the denominator 4. Okay, so it's going to be 43 on 4. I'm not going to work out what 43 times 3 is because I don't need to. Sorry, 43 on 4. Okay, so there's my function in turning point form. Dilation by 3 from the x-axis, translation to the right by 3, translation down by, right by 3 on 2, translation down by 43 on 4. And so therefore our turning point is all about those translations. If we've moved to the left, to the right by 3 on 2, the x-coordinate of the turning point's at 3 on 2, and down by 43 on 4, the y-coordinate of the turning point is at 43 on 4, negative 43 on 4. Okay, last example here. Again, we've got a non-monic quadratic, so the first thing we want to do is factor out the 2, even if it means creating fractions. So we're going to have 2 lots of x squared plus x plus 3 on 2. We want to think about not forgetting about that 2, okay? And we've got x squared plus x. We want to work out what has to complete the square, and then we'll have plus 3 on 2. Okay, so again, we want to halve and square the coefficient of x. The coefficient of x is currently 1. Okay, half of 1 is 1/2. Square that is 1/4. Okay, so we need to add in a quarter and take away a quarter. These first 3 terms now are our perfect square. So we're going to have 2 times, oops, sorry, I don't want to forget it. Don't need to write it in red. I just want in your mind you to see it in red so that you, or some sort of trigger. I must not forget the 2. I must not forget to expand out those brackets again. Okay, so I'm going to have x plus, so remember it's half of the coefficient of x, so the coefficient of x is positive 1, half of that is positive 1/2, so x plus 1/2 all squared, and then we've got minus 1/4 plus 3 on 2, so that's minus 1/4 plus 6 on 4, so we've got 2 lots of, and once again, if you can do that simplification of those fractions in your head, that's fine. In this case, because you didn't need to change both their denominators, hopefully quite a few of you could go straight away to, okay, that's negative 1 on 4 plus 6 on 4, so it's going to be plus 5 on 4. Okay, now finally we want to expand this 2 back in, so it'll be 2 times the perfect square and 2 times 5 on 4. Again, the 4 in the denominator will cancel with the 2, so I'm not going to write that as 10 on 4 and then simplify it to 5 on 2. I'm straight away going to cancel the 2 down with the 4 in the denominator to make it 5 on 2. So we've got 2 times x plus 1/2 all squared plus 5 on 2. Okay. Dilation by 2 from the x-axis, translation to the left by 1/2, and translation up by 5 on 2. So the turning point, if we've gone to the left by 1/2, it's negative 1/2, and up by 5 on 2, 5 on 2. Okay, let's just check our answers using our CAS and to just practice being able to complete the square. So let's have a look at this last example here. Menu 3 for algebra, 5 for complete the square. simply type in your function, 2x squared plus 2x plus 3, comma x to complete the square for x. That seems a bit trivial in the complete the square bracket, but it's important because when we look at completing the square for circles, we want to complete the square in terms of both x and y, and we can do that all at once with this instruction by writing out our expression and being specific about which variables we want to complete the square for. Okay, so there's our answer. Good, that matches the answer we obtained. Let's check the previous one. Menu 3, 5, so 3x squared minus 9x minus 4 comma x, 3 times x minus 3 on 2 all squared minus 43 on 4. Excellent. Okay, any of these others? Menu 3, 5, x squared minus 4x plus 10 comma x, x minus 2 all squared plus 6. So as I said, quick way, efficient way, particularly if you've defined a function, we'll talk more about that down the track, to be able to find the turning point in a nice exact form where the graphing screen can be quite cumbersome, quite slow, quite fiddly, and it will always give you decimals. So if any of those values were surds, for example, you'd have trouble, or even sort of more complicated fractions could be problematic. Okay, so the work to practice here is from exercise 3E. Those questions should give you sufficient completing the square practice.